Okay, video about interrupt-driven SPI on the TMS570. In this particular example, I'm using a 144 pin package, and I'm also using SPI 5. First of all, we should note that not all of the signals mentioned in the documentation and those presented in Halcogen are accessible on this device. So for example, the documentation will tell you there are up to 4 chip selects on an SPI peripheral, and for SPI 5 we've only actually got access to one of those. Scroll down a bit. So this is the list of signals available for SPI 5. So we have our clock. First of all, we have the chip select that I just mentioned, and you can see these are the values presented at the beginning of any list is the default value. This NENA is really only applicable for when you're driving this as a slave and you want a downstream device to be able to use this for handshaking and basically assert this signal and say, can you wait? But we're not doing that because we're just using normal SPI, the normal 4 signal SPI that most people would be familiar with. So here we have SIMO, which they say is slave in, master out. It's worth noting that several other vendors actually put these letters around the other way. So this signal on other devices would be called MOSI, master out, serial in. Texas Instruments seem to want to swap the letters around. Also note that on the SOMI signal, so that's slave out, master in, we actually have 3 of these. We have SOMI 0, SOMI 1 and SOMI 2. And actually if you look in the documentation generally for SPI peripherals, you'll see that the reason they have multiple inputs and multiple outputs is so that you can operate the SPI in a parallel mode. So whereas one clock might clock out, let's say 4 bits on 4 SOMI signals, so you could do quad SPI for example. We're not doing that, and it's again also worth noting that SPI 5 does not provide you with many of those signals, so your options would be quite limited there. Let's go to Halcogen. We should also say that although the documentation is talking about MIB SPI, we're not using MIB SPI, we're actually using SPI 5 here. I've just selected it, and we have a tab here, MIB SPI 5. So the difference is that MIB SPI is a special multi-buffered mode, which is quite advanced and not really what I need. I'm just doing regular plain old SPI, so I'm configuring my options in this SPI 5 tab. Let's have a look at the options. So on the global page, we've got some settings up here for clocking, and then we've got a way of routing through these interrupts. Now actually I will turn these off. I just put those on before I made the video, but the code that I'm running, the configuration, is actually how you see it now. So none of these fuses are made, but after those fuses we then have other fuses which let us pick where those interrupts are routed. So TI provide us with 2 levels of interrupts, so they've called it low level and high level, and this allows us to pick a grouping in here. So we might want to perhaps use the TX and RX complete. We could perhaps put those onto the low level interrupt and then maybe leave all of the possible errors that could happen, have those on a high level interrupt. That's why this is here. I will explain what I have done and why I have done it. I have left all my interrupts configured to be on the high level interrupt, and the reason for this is that, as you will see when we go into Halcogen, when we look at the code generated by Halcogen, we will see that the implementation for each of these interrupt handlers is identical. So really, if we were going to use this feature and pick different groupings here, I think at that point we would probably be rewriting our own interrupt handlers and replacing the ones that are supplied by Halcogen. This is something I do not want to do. I don't want to edit any source code inside Halcogen, so I'll explain how I've worked around that as we look at the code. Why are these fuses not set? If I want to use interrupts, surely I need to know when the TX is complete and when the RX is complete. Yes, I do. I've just done a quick experiment there, and these, if we set these fuses here, we can't set that one, but if we set these fuses here, what will happen is that when the module is initialized, these interrupts become enabled. So these will be enabled the whole time that the module's running. Whereas if we're going to do interrupt driven communications, we don't need to set these here, because when we call the function to start the interrupt driven communications, these interrupts are going to be enabled. So this bit here is not important for your interrupt driven SPI communications, whereas this bit here, whether they're high or low, potentially could be important if you wanted to split the groupings out. If you don't, it's also not important. We'll continue with interrupts and then come back to this to look at the other settings. So if we're going to use interrupts on this peripheral, we need to go to the TMS570 tab, and we need to find the corresponding VIM channel, so that's in the vectored interrupt module. And here, although we're setting this up as SPI, in here they've called them MIB SPI. So you can see here that I've actually enabled both groups of interrupts, the high level interrupts and the low level interrupts, even though if we go back, I don't have anything connected on a low level interrupt. So in theory it's not possible for me to get a low level interrupt. I've just left it like that for now because I've been doing some experimenting and I may want to change the grouping, but I'm just explaining what does what and how you could set it up. So once you've enabled those VIM channels, and when you generate the code, Halcogen will create you some interrupt handlers, which we will look at. Before we look at those, we'll just finish off these tabs. So one thing I like about the way they've approached this configuration is that in here you're allowed to set multiple data formats, and this is very helpful because on my SPI port I've actually got two external peripheral devices, and potentially if you were going to connect different chips to this SPI port, you might find that some of them need to be driven differently, and then when you're using this code inside Halcogen, you can just pass in a structure to the required data format you want. So you might have one IC here that communicates in an 8-bit length, and then you might have another IC that communicates here in a 16-bit length, and you can just pass the right pointer in for the format. So that's a good thing that they've done. Something that I don't like is that the actual API which is generated always uses a pointer to 16-bit data for you to send and receive over SPI. So if in this first case, if you want to just send 8 bits of data, you need to make sure that the 8 bits of data you want to send are in the lower 8 bits of the 16-bit memory address. So if you're then sending multiple bytes, you're going to end up in a situation where you've got an array of 16-bit words, and you need to set your array of 8-bit data into the lower 8 bits of each word. So it adds in a level of work for you to do. You've got to split this 8-bit data into 16-bit memory addresses, or into 16-bit memory address data, but only the lower 8 bits. So it kind of prevents you doing things like a mem copy of a, say, like a structure straight into your transmit buffer, for example. However, you can work around that. I've made a small API function that does that copying that I'm talking about, but would have been nice if perhaps they could have created different APIs for each of these data formats, and then data format 0 could have took an 8-bit pointer. It would have been helpful. The delays, you can delay the time between the clock and the data and other things there, as you can see. I've left most of that alone unless we're actually going to tune this with an oscilloscope and we know the parameters of the device. It's not really important. That normally this will work with just the default set. And here is a way of enabling all of the signals that you want to use on the SPI port. If you remember, I said that not all of these signals are broken out to the device. So we can see here that potentially we've got chip select 3, chip select 2, whereas I showed you at the beginning of the video, these are not accessible on the particular device I'm using. So I have experimented setting the ones that I'm not using to GPIO, but just to see how it affects the code, really. I think either is just as dangerous, because if you set them to GPIO, you could still accidentally trigger these lines. So another thing that's perhaps not ideal, it would perhaps be nice if it knew the part that you were using and then perhaps tailored these options. But these are minor things. I mean, generating the code has given me a usable API from Halcogen, and we'll go and look at that now. Okay, so this is the SPI code generated by Halcogen. We won't go through it all, but these are the interrupt handlers I was talking about. So here's the high level interrupt handler, and above that we have the low level interrupt handler. And if you look carefully, you'll see that the implementation in both of these handlers is identical. As I was saying, it doesn't matter where you route things to, because if you use the interrupt handlers provided by Halcogen, each handler can handle everything. So these handlers will fire every time there's an interrupt. So in the case of, let's look at transmitting data, when we transmit data, we are loading a word or a byte into this one element buffer here. It is then copied into this shift register. Whether it's 8-bit or 16-bit is dealt with in this block here with this mode generation logic, but that data gets shifted out, and once the word is taken from this TX buffer into the shift register, this TX buffer is then empty, and we will see that TX interrupt. So what they've done in Halcogen here, in the case of the transmit buffer empty interrupt, is they've implemented code around this so that you can send a pointer to some data and some length, and this handler will manage loading each word from your data into the TX buffer for you. And it's only going to be at the end, once you've loaded your last byte or word of data into the TX buffer, will they then call back this SPI end notification. So the SPI end notification is for you to implement, and that is to put in your user application so that you know when this transfer is completed. Another file that's generated by Halcogen is this notification.c, and notification.c has some declarations for all of these notifications in, and they use these weak pragmas. And if you don't know, this weak pragma basically tells the linker to use this implementation if it can't find another one, because in your user code you need to provide this implementation. Let's find mine. Here's my implementation which I've provided, and because there is no pragma here, by definition this is strong, it's not weak, so it's going to override this weak definition here. So it's a clever way of providing empty stubs of functions, and then if the engineer wants to implement them, as I have in my case, I don't need to go and delete the other notification in Halcogen. So it's worth mentioning that if you're doing regular SPI, as I call it, where you're sending data and also trying to receive it at the same time, so maybe you're trying to read a register from a real-time clock, and for you to do that you have to clock out some bits, and at the beginning you have to have an opcode that tells the real-time clock that please send me back this data. You're obviously doing a full duplex communication. So this is the Halcogen function call here, SPI send and get data. So when I call that Halcogen function, that is the point at which the TX and the RX interrupt are both enabled. But where I was going with that, what I was saying was that you're doing a full duplex SPI transmission and you have both of those interrupts enabled. In this notification, this is going to fire twice. It's going to fire once at the end of the TX and obviously once at the end of the RX. But it's worth taking note, as we talked about here. This TX buffer goes empty. The interrupt fires into Halcogen, into the Halcogen handler here. And in this handler, once the handler has determined that that is the last byte of data that you want to send, so here he's saying that the length is 0, that is the point at which he is calling that notification. But it's worth bearing in mind that at that point you've put the data into this TX buffer, but it hasn't yet been fully shifted out of this shift register. So when you see that notification that says that the TX is complete, you need to be careful, because it isn't actually really complete at the SPI signals. And I actually had this problem myself, where in my user handler I was putting the chip select back high, because remember I have to manually do it because there aren't enough chip selects on SPI 5 for me, and I wasn't checking it was an RX complete. I was just putting the chip select high, and I was actually disabling the device I was trying to read from. So if you're going to do things in this notification, you probably want to make sure that you're doing it on an RX complete, which really will be when the SPI has really finished. All of the bits have been clocked and the activity has ceased on the SPI lines. And you can tell when you get called back into this notification, you can tell which one it was, because there are some other API functions in Halcogen. So there's SPI RX status and there's SPI TX status, as you can see here. So I've checked that this is an RX complete. One final thing I would like to say is if we go back to this notification file and look at this, we can see that we've only actually been given one set of SPI notifications. So yes, there's 2 notifications, and one is, let's quickly go back to here. So one notification gets called if it's not TX or RX complete. complete, so any of these errors, and then the other notification, which is called end notification, gets called if it's one of these two complete. A problem that I've seen, or another thing that I will have to address, is that when I say there's only one set of these, this notification is valid for SPI1, SPI2, SPI3, etc. So on my system I'm using multiple SPI lines channels. I'm using SPI1 and SPI5, so I'm going to have to change how I work with this notification, because at the moment I've implemented that notification into my user source file, but this is a file that is really only for SPI5, so I'm going to have to add another layer in, I think, where I implement these SPI notifications in a generic file, and then in that generic file I'll need a switch statement that's going to actually look and see which SPI peripheral has called this notification, and then when I know that it's SPI5, then I'll be able to call this handler here, the one that we've been talking about, and obviously I'll have to change the name to a name that doesn't conflict, so I could perhaps call this SPI5 end notification. So I'm just saying that, again, I think it would have been nice if Halcogen had perhaps split those SPI notifications up per peripheral, but yeah, I mean, the user can also do those, just another job that needs to be done. I hope that's useful. It would have saved me some time if I could have seen this video, as I had a few issues to debug through. I hope that's a useful overview of the TMS570 interrupt driven SPI. Thank you very much.